this speaker to vibrate a petri dish containing silicon oil. Now, if I take this toothpick and I make a little droplet on the surface, the droplet will stay there, hovering above the surface. The droplet is actually bouncing, and it'll keep bouncing for a very long time. Now, the reason for this is there's a little layer of air between the droplet and the surface, and the droplet's bouncing so rapidly that that layer never shrinks to about 100 nanometers, which is what it would take for the droplet to recombine with the oil. Now, every time the droplet lands on the surface, it creates a wave. But this is a special type of wave, driven by the vibration of the oil bath. It is a standing wave, meaning that it's not traveling out, it's just oscillating up and down. So the droplet makes the wave, and then it interacts with that wave on its next bounce. If the drop lands on one side of the wave, it is pushed forwards. And as long as the bounce of the droplet remains synchronized with the wave, it'll keep landing on the front side of the wave and getting pushed farther forwards. Droplets like these are known as walkers. The bouncing oil drops have been known about since the 1970s, but only recently has it been discovered that you can use these little droplets to replicate many of the strange phenomena of quantum mechanics. Now, obviously, this is not a quantum system. The droplets are about 1 millimeter in diameter, but you can think of the droplets like quantum particles, say electrons. One experiment that captures the key features of quantum mechanics is the double slit experiment. If you send a beam of electrons at two narrow slits, well, the electrons, rather than behaving like particles and ending up in two clumps behind the slits, they produce an interference pattern, even when you send each electron through one at a time. With walking droplets, the pilot wave goes through both slits, interfering with itself, while the droplet only goes through one slit. The droplet doesn't move in a straight line, though. It's deflected by its interaction with the wave. The resulting distribution of where the droplets end up looks very similar to quantum double-slit interference patterns. Or take tunneling. In quantum mechanics, it's possible for a particle to get through a barrier that it wouldn't classically have enough energy to get over. This has been demonstrated with walkers by creating a shallow barrier under the surface of the oil. Usually the barrier reflects the pilot wave and its bouncing droplet, but in rare cases the droplet does cross the boundary. And the probability of the droplet crossing the barrier decreases exponentially with the increasing width of the barrier, just as in quantum tunneling. Perhaps the most surprising thing about these walkers is they exhibit quantization, just like electrons bound to atoms. Here the walker is confined to a circular corral. The droplet seems to move around randomly as it interacts with its pilot wave. The complex interaction between the droplet and the wave leads to chaotic motion of the droplet. But over time, a pattern builds up. This is the probability density of finding the droplet at any point within the corral, and it looks very similar to the probability density of electrons confined in a quantum corral. All of these similarities are no coincidence. The walking droplets actually create a remarkable physical realization of a theory proposed by de Broglie nearly 100 years ago in the early days of quantum mechanics. He postulated that all particles have a wave that accompanies them and guides their motion, and that wave is actually created by tiny oscillations of the particle. Now, this pilot wave theory was marginalized when the standard Copenhagen interpretation became widely adopted. The Copenhagen interpretation excludes anything that cannot be directly observed, and it says everything that can be known about a particle is contained in its so-called wave function. But adopting this view forces you to give up on some common sense notions, like the idea that particles have a definite position and momentum even when they're not being measured. And it also meant that the universe was no longer deterministic. Randomness is built into standard quantum mechanics. For example, take the double slit experiment. According to quantum mechanics, the wave function of the electron is a superposition of the electron going through one slit and the other slit simultaneously. Using this wave function, you can calculate the probability of where the electron is likely to be. And then when you detect it at the screen, the electron pops up at one point at random that was in that distribution. We say that its wave function collapses instantaneously at the moment of measurement. You can't say that the electron was there before you measured it, and you can't even say that the electron must have gone through one slit or the other. Compare that with the picture provided by the bouncing droplets. In this case, the pilot wave goes through both slits, but the droplet only goes through one. The droplet is pushed around by its interaction with the wave so that the resulting statistical distribution is the same. The droplet never exists in two places at once, and there's no randomness. If there is any uncertainty, it's just due to our ignorance of what's going on. It's not that it doesn't exist. So pilot wave dynamics can produce many of the same results as quantum mechanics. Does this mean that this is really what quantum particles are doing? No. But I think it'll at least suggest that this is possible. These are possible dynamics that could lead to the statistics which are captured in the quantum mechanical theory. And what's appealing about this is it gives you a clear idea of what's going on. You don't have to abandon the idea that the universe is deterministic, and you get particles with definite position and momenta. I think it's great that we have two competing theories for the same experiments. And they both ask you to accept odd things, just different odd things. And it comes down to what you're comfortable with, really, whether you prefer the Copenhagen interpretation of standard quantum mechanics or a pilot wave theory. Let me know what you think in the comments. Do you like the pilot waves? I mean, it's definitely a very appealing picture. Whether or not it corresponds to reality, that remains to be seen. Hey, this episode of Veritasium was supported in part by viewers like you on Patreon and by Google's Making and Science initiative, which seeks to inspire people to learn more about science and pursue their science goals. Now, I know someone else who is pursuing their science goals this week, and that is Destin over at Smarter Every Day. He and I were looking at basically the same phenomenon, but he was looking at water droplets and why they don't coalesce. So if you want to see how that works and how it works in space, go check it out on his channel over at Smarter Every Day. And as always, thanks for watching. Looking at only one frame per bounce, you can see how the droplet's motion is guided by the wave it's effectively surfing on. And the wave remains even if the droplet disappears, as happens sometimes if it encounters a little bit of dirt. What's really cool about this is the wave actually stores information about where the droplet has been. This is because every time the droplet bounces, it creates a new circular wave centered on its present location. And that wave adds to the existing wave field on the surface. So as the droplet moves, the waves it makes keep adding up, storing the information of where it's been. In fact, you can actually get the droplet to land on the backside of the wave. So now it's pushed backwards, and it retraces its steps, erasing each wave it made previously one at a time.